Let's use the 6-step procedure from your textbook to graph this nice rational function. Okay, well, let's remember what this was. Again, page 321. We're going to just roll through the steps. So to start ourselves off, absolutely the first thing we should do is we should factor everything. So if we can factor this, we should factor it. We know that this, I guess, x squared plus 1 is factorable over the complex numbers, but that's not what we want to do. We want to factor it over the real numbers, and we know that we can't factor that over the real numbers, so we just don't, and that's factored. So we can get on with it. First step, we want to find the domain. So again, domain of a rational function. Anytime we have a rational function, the domain is the set of all of the real numbers so that the denominator is not 0. So in this one, we want to take away -3. So we can say set of all x such that x is not -3. Okay, excuse me. We can write this right in interval notation. If we want to take away everything except for -3, we go -infinity to -3, union -3 to infinity, and then we have it in interval notation. We've got our domain. Okay, second, we want to reduce the function. So if we can reduce, we will. Reducing this means just essentially canceling common factors. So we see that we don't have common factors. So we're done here. All right. Step 3, we're going to find x and y intercepts. We can do this pretty quickly. X-intercepts, we've been doing this for a while. We're going to solve where the function is equal to 0, and y-intercepts, we're going to evaluate f of 0. Okay, so we can crank on through. Solve where the function's equal to 0. So again, there is our function up there. Let me get rid of this. So we want to know where is this function equal to 0, which really boils down to where the numerator is 0. So we got x squared plus 1 equals 0. So we want to solve that. We can try to subtract 1 from both sides. Then we've got x equal plus or minus square root of -1. So this is plus or minus I. So we say that this is no real solutions. So that means that there are no x-intercepts. Okay, because there are no real solutions to that nice equation, there's no x-intercepts. So that's gonna be all right for us. Evaluate f of 0. We're finding the y-intercept now. F of 0, we're just going to crank a 0 through the function. We've got 0 plus 1 over 0 plus 3, so that's 1/3. Our y-intercept is 0, 1/3. All right, we have x-intercepts, don't exist, and, well, don't exist in the real numbers. And the y-intercept is 0, 1/3. Okay, so now we're on to step 4. So we're going to determine the location of any vertical asymptotes or holes in the graph, if they exist. Analyze behavior of R on either side of the asymptote. So we're going to do this analyze the behavior at the last step, but certainly right now we can determine the location of any vertical asymptotes or holes in the graph. So let's take a look on page 306. This is going to tell us what to do. So if we've got let's look at our function at the same time. So if we have a rational function that can be written as a fraction where p and q have no common zeros, so essentially what this means is it's reduced. So if our function is reduced, and c is a number that is not in the domain of R. So in our case here, our c value is -3, right? Because that was our domain, everything except for -3. That was our first step there, right? So just satisfying the theorem here, our function is reduced, it's got no common zeros. We've got a number that's not in the domain, so that's -3 is not in the domain. Okay, so if our denominator is not 0 at -3, then that's a hole. So what this is saying is that once we find our domain, if we factor it away or cancel out the domain restriction, then that's going to be a hole. Well, the domain restriction stayed here, right? So we didn't do anything in step 2. Step 2 is reducing the fraction. We did not remove any domain restrictions, so that means that they're all vertical asymptotes. This is kind of a pretty mathy wording of saying just that. You know, if we cancel a factor in step 2, that's going to be a hole in the graph. And we can say it in a mathy way here on page 306 with theorem 4.1. Okay, anyway, we didn't have any of those canceled out. Our denominator is still 0 at x equal -3. So that means that we have a vertical asymptote. So 4, we have a vertical asymptote at x equal -3. Okay, so 5, we're going to determine end behavior. So our end behavior, that's another way of saying find your horizontal asymptotes. So let's look at this horizontal asymptotes business. Well, let me get that function back up there. All right, so with this one, we've got 3 options, right? So we've got this page 308. So we have a rational function where we got a numerator and a denominator. Okay, leading coefficients are a and b. So if their degrees are the same, then the horizontal asymptote, well, let's not even look at that. Let's just look at what we have, right? The degree in the numerator is 2. The degree in the denominator is 1. So if the degrees are the same, well, that's not our case. If the degree in the top is less than the degree of the, nope, that's not our case because the degree in the top is bigger. If the degree of the numerator is greater than the degree of q, which is the denominator, then the graph has no horizontal asymptotes. So that's where we're at. We don't have any horizontal asymptotes. So we say no horizontal asymptote. However, we do need to check if we've got what your textbook calls slant asymptote. So let's check this out. This is theorem 4.3 on page 312. If you're writing this in your notes, or if you are taking notes over this section, really we can combine these two things. You know, we have the first one, the second one here, and then combine in the slant asymptote deal. Because this isn't, you know, that's not exactly necessary. But anyway, let's check this out. Suppose we have a rational function. Again, we're setting ourselves up just like the last one, except the degree of p is exactly 1 more than the degree of q. And that's what we've got here, right? The degree of p, the numerator, is 2. The degree of the denominator is 1. So that's exactly 1 bigger. Okay, then the graph of our function has a slant asymptote at y equal big L of x, where big L of x is the quotient obtained by dividing p by q. Okay, so we're just going to do long division. That's all that's saying we do. And we only care about the quotient. So we're going to do long division, where we have, we're going to divide x squared plus 1, divide by x plus 3. So we can, depending on our comfort level here, we can either use long division or synthetic division. I'll probably just use long division here, just to spare any confusion. Anyway, no horizontal asymptote. We're going to use long division to find our slant asymptote. Okay, so we're going to divide. If we would write our function okay, let's use long division, and we'll do the work down here. So we got x squared plus, again, well, maybe not again, for the first time in this video, we can't forget to put a placeholder for any missing values here. So x plus 3. So we got to have a placeholder there. Don't forget about that. Okay, so we'll just crank right on through this long division. X goes into x squared x times, and then we multiply x times x plus 3. So we got x squared plus 3x. And then we subtract the whole thing. Here's where you're going to make your mistake. Every single time I see this in a student's work, kind of gets a little cringy because we make a mistake so much. We want to subtract all of it, right? The whole thing. So we're subtracting 3x and we're subtracting x squared. So 0 minus 3x is negative 3x. X squared minus x squared, that's 0. We're going to bring down our plus 1. All right, now we say x goes into negative 3x negative 3 times, and we multiply negative 3x minus 9, and then again we subtract the whole thing, not just that front piece. We want to subtract the whole thing. Okay, so we've got 1 minus negative 9, that's plus, so we got a 10, and then that's 0. So what we've shown here is that we can write our function as x minus 3 plus 10 over x plus 3. All right, so we used long division to rewrite our function as a quotient and a remainder, right? So the original function, we used long division here to show that we can rewrite it as a quotient and a remainder. So our quotient really is the only part that we're concerned with here. So that's going to be our slant asymptote. Y equal x minus 3 is slant asymptote. Okay, so what remains here is we ought to check if our graph touches that slant asymptote. This part is kind of overlooked sometimes, but it is important when we are trying to end up trying to draw our graph at the end. It's going to be important for us to know whether or not it touches there. So, does the graph touch? So asking this question is the same as asking this question. Does our function equal x minus 3 have solutions? And this is going to tell us whether or not our graph intersects this line. So we can go ahead and solve that fairly quickly. We've got our original function, and is that ever equal to x minus 3? So we're going to do what we usually do when we solve these, multiply everything by the denominator just to get rid of it. And we're gonna have our result pretty quickly here. These two, they cancel out, so we've got x squared plus 1. We know that this is the difference of squares, right? If we've got the product of two conjugates, it's the difference of their squares. It's one of our factoring rules. So we've got that. And then we can subtract x squared from both sides and show that we have no solutions. So does not touch. So when we're drawing our graph at the end step, which we're going to do presently here, we know that we do not touch that slant asymptote. Okay, wonderful. So step 6 is just to, well, essentially just put all the pieces together. Let me grab a blank sheet here. Okay, so step 6 is to essentially just put all the pieces together and connect the dots essentially. So we can do this. We'll just go step by step. So our domain, that's wonderful. Didn't do anything there. X-intercepts, recall that there were no x-intercepts. We did have a y-intercept at 0, 1/3. So let's put that right there. Okay, vertical asymptote at x equal -3. So x equal -3. I almost made a horizontal line there. Okay, so there's x equal 3. No horizontal asymptotes. Our slant asymptote was x minus 3, so y equal x minus 3. Okay, so that's okay. And we've got that stuff, okay. Now we have to decide what the rest of the graph looks like, because that was all we had to go on, right? We had x and y intercepts, we only had a y-intercept. We only have one vertical asymptote, and we've got one slant asymptote. So we can go through the rest of this process, maybe by plotting a few points, or by just kind of noting what needs to happen, right? So if we're just concerned with what's happening in this branch of it, we can put together some of the stuff we already talked about. So we know that the graph of our rational function is not going to touch this line, but it is going to approach it, right? So if I come out of this point moving toward the right, I can't cross this line, and I can't cross the x-axis because there are no x-intercepts, and we all already showed that we can't touch this, so we just have to approach it. So we're going to go toward it like that. And similarly, on the left-hand side of our y-axis toward x equal -3, we're going to have to go up toward that vertical asymptote because we can't go down, right? We've already showed that we don't have any x-intercepts, so it's got to go up. It can't go down. Okay, so now what remains is just what's happening over on this side. Well, we could probably reason our way through this as well, right? It's either going to be up on top of the line y equal x minus 3, so it's either going to be up here or it's going to be down below. Well, if it was up top, we're going to have to approach the vertical asymptote, and we're going to have to approach that slant asymptote. So if that were the case, we're going to have to cross that x-axis. But we showed, I think in step 3 showed us that we have no x-intercepts. So this possibility can't happen, right? If it were up in this region, then we would have to cross that x-axis. We already showed that that couldn't happen. Well, what that implies to us is that the graph has to be down here, and it's gonna, it's gonna look something like this. What would probably be in your best interest is to just maybe take and find f of -4, and then we can put a better point on there. But in the context of what we're doing and the limitations of our system, homework-wise, super rough sketch is fine. We could probably plug in a couple of points and just not even do any of this process if we have all the 4 graphs in front of you. But we will need to do this by hand just to show that we actually know how to do it. Anyway, we drew our beautiful graph. We might improve it by putting up another point, but at the end of the day, for this particular exercise, I think we can get away with not.